Okay, we already talked about this in class, and this page will be posted online, but I just want it up there to kind of review a little bit, so I'm just going to add a few comments in case, maybe there's a part you're a little confused about and you just want to hear me talk through it again, and this is right for you. So when we did our back-to-back graphing activity, we tried to describe graphs to someone without looking at them, and we kind of developed our own words and things that we said that we thought were helpful. And what we want to set the stage for is when you talk to another mathematician, or you're trying to be more formal in your language, we have certain words that have a common meaning, and so we want to be as specific and precise as we can. So this just briefly goes over some of those words, and as we start describing graphs moving forward, let's try to use this vocabulary moving forward. So starting off, direction, really simple. Increasing, decreasing, or constant has to do with, as you're reading the graph from left to right, which one it is, and it's possible you might have both. If you think of like a parabola shape, something like this, we would describe this as decreasing then increasing, right? So it can go both ways. We can have both an increasing and decreasing graph. Okay. In addition, we might describe our data set specifically regarding our domain, is usually what this is restriction of. And there's 4 main steps that we could have. The first is called continuous. The way to think about continuous is that if I put my pen on the page and start drawing, I never have to pick it up. If I can draw the entire graph without ever having to pick up my pen, it is in fact a continuous graph. Something like this would often be anything that's connected, like a line or a parabola, things modeling that would reach every value, so like temperature during the day. You would have a high and you would have a low every day, and you would hit every temperature in between the two. So something like that would be continuous. Discrete data, on the other hand, is usually just dots or specific points, and this is often for items that only come in set quantities. So an example I love to use is, suppose you're going to the store to buy t-shirts. You're not going to buy half a t-shirt, right? You're going to buy 1 t-shirt, 2 t-shirts, 3 t-shirts, 4 t-shirts. So it doesn't make sense to connect all the dots because you're not going to have all of those fractions available. A step function is what we would observe when the values jump, like a discrete graph, but they might last for a little while. This is usually with time on the x-axis. Best example I can think of here would be if you think of like the price of a postage stamp. It jumps in whole cent increments, but it might be for different amounts of time. It might jump to 50 cents and be there for 6 months, and then drop down to 48 cents and be there for a few years. So it would kind of be in steps. And then finally we have what would be called piecewise, which is when you have very different types of functions. Maybe you have parabolas and lines or something even crazier, and you're only taking a piece of each function. So rather than each function going from negative infinity to positive infinity, you would take just a piece of it. So we'd have those 4 ways of describing our data set. These function families, or parent functions, I'm going to go super fast on because we're actually going to look more in depth later. But again, I wanted you to have them ahead of time just to kind of front load them as a resource. I'm going to go through them pretty quickly. The first 3 you've definitely seen before. Linear, anything to do with a straight line. Exponential, this would be things for like decay and growth, bacteria models, population models, finance, markets, bank accounts, things like that. Parabolic, the pathway of a projectile, rainbows, anything that kind of makes that U shape, a lot of times will be parabolic in nature. We have cubic functions, which is the next level up. If this is x squared for parabolic, then a cubic would be x cubed. We have our root functions, or square root functions, and absolute value. These are the V shapes. These are ones that you've maybe have started to see the last couple of years, but not tons. We'll investigate them more this year. We also have what's called rational functions. This is anytime you have x on the bottom of a fraction in your formula. And we'll be taking a look at those in the next couple of days and investigating them more later. But anytime you have x on the bottom of a fraction, you're going to get this weird effect with asymptotes, which, if you don't recall, is when a line approaches or the curve approaches a line but doesn't cross it. This actually has an asymptote on each axis right here. And then finally, the trig functions are periodic. So this is your sine, cosine, tangent. Anything that's cyclical in nature, goes up and down, ocean waves, sound waves, light waves, anything that's periodic in nature can be modeled using these trig functions. And then last but not least, I just wanted to list several details that we can use to describe graphs in general. X and Y intercepts are always fantastic points for reference. As a general rule, if I ask you for X or a Y intercept, I want to see the ordered pair point. I don't just want to see 3 or just see 2, but I want to see you actually list out the ordered pair, because that's what they are ordered pairs. We might also talk about the steepness of a slope. Is it less steep or shallow? Is it more steep? Things like that. A lot of times for graphs, we're interested in maximum minimums. Those are usually our answers in problems. What was the maximum height of the kicked ball, that type of a thing. Domain and range are great values to keep in track of. I actually have another video on that you can check out. Domain is our x values, range are our y values. Asymptotes are very, very important. They basically are a line where the curve gets closer and closer and closer to without actually crossing. So asymptotes are fantastic. And then when in doubt, just always list extra points. A lot of times intercepts, max mins, and restrictions on domain and range will get you pretty far, but sometimes just needing to list a couple other points will be incredibly helpful. So this page will be posted on the website as well. Check it out, and if you have questions about any of these pieces or what the words mean, please ask.